I'm pleased to be here today. My name is Steven Zagorianakos from Netronome, and I have the pleasure of talking about massively parallel RISC processing with transactional memories. Before I get into the presentation too much, I just want to do a shout out to Rajiv Vidhasavaran, RV as he's called, for his collaboration on this material. Today we're going to discuss how do we build up a RISC-V into thousands of processors. We're going to discuss transactional memories. We're going to do a walkthrough through an example application utilizing the transactional memories in RISC Harts. We're going to start at the full chip level and work our way down to an island, cluster, and groups of RISC-V Harts. We're going to talk about the modifications that are required to tailor the RISC-V for our embedded application, which is a SmartNIC marketplace, and then maybe talk about a little bit of summaries. Before I get too far into the heart of the application, I'd like to say a few words on multiprocessor cores and memory hierarchies. In the past, such systems needed to utilize a custom approach or shoehorn in a standard processor. With the advent of the open architecture RISC-V, we have an opportunity now to merge the two. We have the opportunity to tailor the instruction set and customize the optimizations we want to make to the RISC-V itself. This allows us to have the ability to support multiple embedded applications. The transactional memory part of this gives us a second opportunity to tailor the embedded systems and put the memory and memory hierarchies where the data needs to arrive in the systems. What is transactional memories? We speak a lot about, in the current architectures, about cache architecture, where we try to get the data as close as possible to the CPU so the CPU can have the ability to work on the data with the lowest amount of latency. And that works well for most applications. Transactional memory switches that around. It actually tries to put the execution unit as close as possible to the memory and have the execution unit execute on the memory itself. There are several examples of operations that this works well with. Fire and forget. What do I mean by that? A command that you can issue to the memory that you don't want a response back. Several applications that work well for this. In networking, we have to keep track of statistics about the packets, the system, and other things, which require a multiple of semaphores or atomic operations to be performed to the memory structure. With a transactional memory, you can issue one command and multiple of the statistics will get updated in one shot. Operations that require collaboration between multiple CPU Harts. It basically allows the memory itself to be the sync point of the operation versus having to go back and forth between the Harts to synchronize data up. How does it actually work? A command is issued from a CPU, RISC-V in this case. The command includes the information that's required for the operation. It includes where the data resides in the CPU that the operation needs to have. It includes the memory range that the operation runs on, and then it includes how to terminate the operation, whether the processor needs to be signaled or woken up when the operation is done, or it doesn't need any return information. The type of transactional operation, some of them are listed here on the chart, could be as simple as atomic operation, CRC calculations on a range of memory location, all the way up to doing a full decrypt or encrypt of your packet coming into the system. One of the things I do want to mention, the goal of transactional memory operation is not to affect the normal C execution of the code. So we follow all the standard constructs for doing standard C execution. So how do we build up a full chip with 1,000 processors on it? You can't have them all at the top level of the chip. So we have the concept of implementing islands, which are self-contained units that allow for building blocks that can be placed anywhere within a fabric. They include all necessary components to do the testing as if they were a single chip. The islands allow us to implement a building block approach from very small to very large chips. The memory hierarchy here for embedded applications, we require some of it needs to be cacheable, some of it isn't cacheable. And one of the things that I want to go mention here is the reason we have the memory hierarchy support. We can support all types of memory transactions, spread the transactions and data bandwidth load across locality of application processing. So we can distribute the load of the system as the data comes in. And I'll go through a few examples of that when we walk through the life of a packet. The basic building blocks of our chips come into three types. One is how do we get the data in and out of the chip? They have the I/O capability. Their interfaces, the network interfaces, PC. If we're doing coherent buses, it would be like a C6 or some other coherent protocol. It would also be the configuration bus that we have here and the host interface buses. So data in and out of the chip. The second level is actually the memories. What we're showing is at this level is two types: direct access memory, which is SRAM based, and cache backed memory, which can either be DRAM back cache or host memory back cached. And then, of course, islands and islands of RISC-V processors. Basic flow of a packet. I just wanted to give you some idea of how a packet would travel through the system. I'm going to start with the example is we have, assuming today's marketplace is currently 100 gig NICs are commonplace. We produce 25, 50, and 100 gig today, and we're looking to going into higher speeds for our next generation chips. A packet comes into the system through the network port. What does that mean? 100 gig packet, that means a 64 bytes every 3 nanoseconds. A load balancer of some sort, which is a part of the hierarchical memory structure, decides what memory to assign that packet to. It's usually one of the SRAM memories that are sitting in the four corners of this block diagram. The packet is pushed to an SRAM. Once the SRAM has received the packet, a transactional memory unit that controls the flow of the packets assigns it to a processor. It will autonomously push the appropriate amount of metadata and first n number of bytes of the packet to the assigned processor and wake that processor up for processing. I don't have time to go into all the processing that happens today, but I'll just say there's a big magic block there that basically works on the packet, determines what to do with the packet, whether it has to be encrypted, decrypted, what's next for the packet, but eventually the processor determines the packet is finished processing and has to egress the system somewhere. It will send a command through a transactional memory unit to schedule the packet for the appropriate egress port, whether that's a host port, whether it's a network port, whether it's a further processing on another processor within the same chip. So most of the time I wanted to spend today is how do you build up the RISC-V complex to get 1,000 processors. We're starting from the top level and working our way down. So we have a concept of an island. The island is made up of local memory, clusters of RISC-V processors, and slices of cache. The operations are divided into two parts. Standard data processor type applications that are load, store, cacheable, that utilizes a tile-link protocol and introduces, the same level 1, level 2 cache that everybody else is used to, backed with a cache on a memory somewhere else higher in the system. And we showed it as the level 3 cache on the previous slide. The other types of operations that are required, we mentioned transactional memory operations coming out of the left-hand side of the block diagram here. Those also use the load store instruction set from the clusters, but they form operations that get executed elsewhere, close to, as possible to the memory. And then there is a operation that allows the waking up of the RISC-V processor. The cluster is made up of groups of RISC-V processors. In this example, each group contains 10 processors. The processors have the ability to go in several different directions. I mentioned transactional memories. We utilize the island bus interface, in this case, to generate the transactional memory operations, and a data management flow control to support the multiple cache operations for the tile link interface. At the cluster level, we can support both remote cacheable coherent operations and transactional memory operations. And we roll up the groups in groups of 10 to form 40 at this level, and at the next level, that goes into the island, which you have multiple of these groups. That gets us up to greater than 100 processors per island, and then n number of islands per chip that allow you to get over 1,000 processors per chip. So what the group is basically made up of the actual RISC core with some extensions. We've actually, one of the big things is if you're going to put this many processors on a chip, you got to be very cognizant of the size of the processor, the size of anything you put on the processor. So a couple of pieces that I wanted to talk about that we've actually simplified. One being the multiply unit. We've actually reduced the size of it and reduced the overall performance to have a balance between size and performance for the multiply. We've stripped out the debug capability out of each of the single cores and moved it as its own peripheral block so that one debug unit supports a group of cores to save size. It still gives us the full debug capability about debugging any single core on the chip or any group of cores there, but we can't look at all 1,000 cores at the same time. We evaluated several different cores. We settled in on the RV32IMC and wanted some additional features for bit manipulation commands. We utilized the custom instruction to manage the memory binding operations. One of the limitations of a 32-bit machine that we selected is the fact that it only has a 32-bit address, which wasn't extensive enough for us. So the binding operation that we do that goes from a local CPU address into a global CPU address expands that address space to greater than 48 bits of address. So we can have a reasonable address space for the processors to access. We also use the custom instructions to support the ability to do the transactional memory operations. So that's the method that we're using to set up the instructions and return the results of the instruction back, along with the signaling method. We also need some level of user mode and low-level machine mode operation. So we're supporting both of those. One of the examples of that is In some applications, we want a higher level of security to not allow every processor in the system to have access to every feature of the system. We can use the low-level mode to trap transactional memory operations and only allow the user mode to execute those through the machine mode. So I just wanted to put a slide up here that basically talks about what I just said of what are the feature modifications and what are our plans of actual implementation. So I'm not going to go reread this. I'll let this stand as its own. But what I do want to go say, the RISC-V architecture opens up a world of possibilities. And the amount of people here today just demonstrates that a lot. We, in the past, over the last 10 years, we ended up doing our own custom processors. And we're in the process of transitioning from an internal custom solution to an open solution. And the RISC-V is the first opportunity that allows us to tailoring a standard solution to fit our needs. And in summary, the RISC-V solution can be tailored to meet the needs of embedded applications for suitable choice of an instruction set feature, privilege modes, and debug modes. And the use of highly optimized transactional memories lends itself to doing a lot of the operations that are more centric to the memories versus the CPUs. And I think the interaction of both of those systems allow RISC-V and SmartNICs to go way over the 100 gig capability of today. One of the things I do want to mention, is the ODSA, which is a consortium that we're trying to start up to try to expand the capability of moving open source into open interfaces to allow that standard chip interconnects can be done in a more reasonable, implementable way to help the industry. But you can come by the booth and pick up all the information on that. Thank you.